Liv and Lee, I love that you're together and you let me know that. I usually do ask people if you don't mind, put your cameras on. It just makes me feel less. Thank you, Rhiannon. Like I'm talking to nobody, that I can see people. So appreciate that. Oh, wait just a minute to see if anybody else is joining us, if they have any issues kind of joining. Hi, Maria. Liv and Lee, can I see your happy biochem faces? Connor's joining. Hey, Connor. Oh, see, I should just wait a minute.
Hey,
There we go. Hi, Connor.
how's it going?
Yeah, it's going. It is 9 o'clock and I'm on a Zoom call with fellow biochemists. I guess that's a good thing. Oh, so somebody, who was this? Who just sent me? This may have been, nope, Connor, that was you that sent me that text message. You figured it out. All right, I'm going to go ahead and get started. Just, I usually try not to make these longer than an hour. This one may even be less than that because truthfully, there's less content and there's just one learning unit, but it's it's kind of a breadth of stuff. So I want to make sure I give you guys enough time to ask questions if you have any. I'll sort of share with you that I'll run them the sort of the same way that I've done in the past. I am going to ask a question too. I forgot to do this in class today. There we go. There's a camera for Lee. Are you with Liv too? Oh, there she is. Hi. Okay. Um, so the exam is meant, all of my exams are meant to be done in 50 minutes, but I know sometimes they can be stressful and all sorts of things. So in general, what I like to offer is, and people generally have sort of a situation where they either can come in a half an hour early or they can stay a half an hour late if they want. Again, they're easily done within a 50-minute period, but I know some people can stress out. So think about that. I want to make sure to hear from everybody tomorrow. If that can't work for you, where it's like you have a class at 8 and a class at 10, in addition to my class at 9, where you wouldn't be able to choose to come in or stay later. Now, because there is a class that comes in right after ours, Dr. Jones's class, we just may have to move if you're going to choose to stay later. So we can talk about that tomorrow, but I wanted to sort of throw that out there. That is something that I offer in Biochem 1 to just give you guys some extra time if you feel like you want to take it so that you're not stressed and all of that. Second thing is, I'll just let you know how I generally run these sessions is I'll share my screen. I'll sort of go through the review, the study guide that I have. We'll look at the homework questions, and then I'll look through the notes. And it might be sort of an assembly of sort of going back and forth with those. And I want you guys to interject. It's not meant to be a completely passive sort of situation. Interject, ask questions if you want clarification on things. I'm trying to figure out, hang on, somebody has Daisy right now. Let me just text her real quick. She's over playing with her brother next door. That would be great. I'm in class Zoom right now, but John is downstairs. You can just bring her back to the yard. All right. So, but before that, let me just ask if there's any general questions on things. Nope. All right. So she's going to share my screen. All right. And all of this stuff is available to you guys. It's in a couple different spots. I am in the process of trying to create these Google Sheets that have all the information, but you should be able to find everything you need right now on Blackboard. Again, you may need to go back to last year's Blackboard space for kind of a more organized presentation format for the content. But remember, this is just Learning Unit 1 that we have here. So I've got the study guide open here. If you didn't know where the study guide stuff was, there's a tab here called Exam Preparation. So if you click on that, you'll find study guides, and I've actually posted links from previous review sessions. Probably what I'll start doing is accumulating these just as links. You'll be hearing the same playbook. They're generally not different. But I have those from previous years. So this is the study guide that I've got up here. My plan is I'll go through each one of these pieces. I'll sort of share with you like what you need to know with that. I'll show you stuff in the notes that you need to know, and then we can go over homework questions, and we'll sort of go back and forth like that. Interject questions as they come up. Don't hesitate to just interject when you have them. But so starting here, and again, this it's only a one pager for the study guide. So equations that you need to know. You need to know how to write acid-base equilibria. So whether it's looking at a specific molecule or it's looking at, and I might kind of go back and forth here with stuff as it's relevant from the notes. So this kind of stuff, like if you were given a specific acid or a general acid, and based on whether it was a strong acid or a weak acid, that you could write an equation that sort of highlights what's going on, understanding that acid-base equilibria, basic fuel equation, your blood buffering system, and your breathing equation. Okay, put a giant star next to this slide right here. This is a super important slide, right? This is sort of what our case study was about. So be able to recreate aspects of this, right? There's three equations that are sort of, well, I guess there's two equations and then sort of a process. I want you to know the fuel equation. I want you to know this equation that has to do with the enzyme carbonic anhydrase, and then what carbonic acid can do as a weak acid. So a number that you need to know, an enzyme name that you need to know. And then again, it's not really an equation, but the purpose of breathing, right? Take oxygen in, CO2 out, be able to think about what happens if you're under either a hypo or a hyperventilation state, how that can lead to respiratory acidosis or alkalosis, right? So this equilibrium shifting. So again, that's sort of all of the equations that you need to know here from a qualitative standpoint. We'll talk about some quantitative equations that you need to know as well. But I want to pause there. I'll generally pause at places and just make sure if you haven't interjected with a question, if there's something that you'd like to ask, have an opportunity to do so.
I meant to ask this in the beginning and then forgot. Is the structure of your exams, is it like some multiple choice, some short answer? Is it all short answer? Like what?
Good question. So this first exam, it's a little bit of a grab bag worth of stuff. There are some things where it is a literally fill in the blank. So an example of a question might be, what is physiological pH? 7.4. That's literally just writing down an answer. It might be asking you a question about, like for example, these two, I'll just give you these as an example. Like you need to know the Henderson-Hasselbalch equation. You might see an equation or a question where you just have to write it down and explain the parts. Or you might have a computational question where you actually have to use the Henderson-Hasselbalch equation to answer a question about what's the pH of this solution. Same thing with the two equations you need to know for free energy. So it is a combination. There's no multiple choice. And it is a combination of maybe short answer, short response, and some lengthier questions that might be a little bit more computational. I will say what I tend to do for the rest of the exams in the semester. This one is a little bit more of a grab bag, so I don't tend to do this. The rest of the exams will generally be largely, I shouldn't say largely, there's a significant portion that is literally one word fill-in responses. So that there's something that you can get in quickly. It's sort of like a rapid response. There are some of those kinds of questions here, but many fewer than you'll see later. And so for future exams, what I'll do is when I provide kind of a framework, I actually take my exam and I remove all of the questions that are under a subset, and I'll be like, okay, there's like 6 questions that all have to do with this topic. So your third question is all going to be about this area. So you sort of have a framework of what to think about. Does that help, Rhiannon?
Yeah, it does. Thank you.
So I sort of went through this piece quantitatively. You need to know the Henderson-Hasselbalch equation, how we can use it to calculate the pH of a solution, or how we can use it to calculate the amounts of different things that we'd put in. So we're going to deal with a lot of these calculations tomorrow in lab math. So hopefully if you didn't understand some things on the homework, we'll get to them on our lab math. With regards to the aspirin overdose, just sort of remember the concepts of how we use the Henderson-Hasselbalch equation to talk about solubility. And that was using the Henderson-Hasselbalch equation with the weak acid, that is aspirin, to look at whether it was in its protonated form, which having a carboxylic acid functional group was going to be neutral charged, and then its deprotonated form, which with the carboxylic acid functional group would make it negatively charged. So again, we could use the Henderson-Hasselbalch equation to relate the amount of uncharged and charged species dependent on pH, and we use that to explain why we would want to do a gastric lavage at high pH. We second situation where we use the Henderson-Hasselbalch equation, used it to talk about how blood pH represented, when we changed blood pH, that was really represented by different concentrations of carbonic acid and bicarbonate in the blood. And we sort of highlighted that there's a couple of different systems that function together to modulate blood pH. We didn't really talk about phosphate at all, but then that carbonic acid system is a way that we can regulate blood pH. And going back to this slide, since I think it's still up here, CO2 levels that get put in your blood have a significant effect on the amount of carbonic acid that's there, and thus the amount of H+. And we talked about the different ways that we can affect the amount of CO2 that's in your blood, right? We can have metabolism contributing to it. That would indicate that we'd be putting ourselves in a metabolic acidosis state. Or we can have hypo or hyperventilation, either increase or decrease the amount of CO2. So being able to understand how equilibria shifts depending on whether we're adding in CO2, shifts to the right. We're going to increase H+, which means we decrease pH. Or if we're finding a situation where we're removing CO2 from our blood and from this equilibrium, equilibrium shifts to the left. And in that case, we're going to be decreasing H+ concentration, which means we're increasing pH. So be
Dr.
able to,
Burnett.
yes.
Oh, while you were on that slide, would you be able to go over how the bicarbonate drip helps to change this equilibrium?
Yep. So, and I'll get to that in just a second. One thing I want to highlight is a very common thing that you will see with exams that I give is there's a concept that we learned about in a certain situation, and then I ask you to apply those principles in a new situation. Okay, so you want to be able to think about, this case was about hyperventilation. If I were to ask you a question about hypoventilation, you want to be able to think about the same system, but about how those different circumstances would affect things. So to Connor's question, how would bicarbonate affect things? What I'm actually going to do is I'm going to flip to the questions from the case study, because that's really where it was relevant. And I think so this group's kind of like dealt with why the bicarbonate drip was necessary. But I think Connor, you and Allie actually sort of got to, oh, you guys were doing that with gastric lavage. So our third group here, this was Lee and Liv. You guys were sort of talking about what's sort of happening here, right? And here is the equation that allows us to think about what's happening to bicarbonate. So Connor, I'm just going to call on you here because you had asked this question. So does it make sense to you when we are hyperventilating, this equilibrium shifts to the left because we are expelling CO2, and that depletes the bicarbonate that we have. Now, the last group, which was Rhiannon, and she and I sort of tag teamed and did this together, you can actually calculate based on the blood pH, which is increasing, the amount of bicarbonate that you have, and it's getting decreased. And so that's making us not have as good of a buffer. So all we're doing is replenishing the bicarbonate that's there. Because remember, two things we want to have that make for a good buffering system. You want to have relatively equal concentrations and relatively large concentrations. And so if we sort of look at the math that we have when our blood pH goes up, and let me see, I think I put some slides in here to sort of help us. When we think about the ratio that we have here, when our blood pH goes up, we are sort of getting skewed in terms of our ability to sort of buffer our blood. So what we're really having here is we're having a ratio that's getting much greater than 10. But the important piece and why we need the bicarbonate drip is not only does that ratio change, I'm looking for this calculation, but the absolute amount of bicarbonate changes, right? So here's our patient. It told us that blood values of bicarbonate were 21 millimolar. In a normal patient, they should be 22 to 26. So we're just replacing that bicarbonate because it was being removed by all the exhaling that patient was doing. Does that help?
Yeah.
All right, I'm going to come back over here. Frequently there's going to be numbers that I want you to know. I am not big on memorizing a lot in this class that's not going to be useful for sort of your understanding. So obviously we needed to know pKa values of carboxylic acids, protonated amines, and alcohols. You already had to know those for your functional group quiz. I do want you to know the specific pKa value for carbonic acid. 6.35. Interestingly enough, it's a bit higher than our normal functional group for carboxylic acids. But this is important because it allows us to have a pKa near neutrality. Remember, when you are picking, this is another one of those important things. If you had to pick, flip to these slides here for a second. When we're talking about buffers and we looked at this table, right? If you had to choose a buffer system that was going to work around physiological pH, 7.4, you'd probably pick something that runs between 6.4 and 8.4, right? And so bicarbonate is sort of part of that. The phosphate system is part of that as well. So I do want you to know the carbonic acid pKa of 6.35. Physiological values, I told you pH 7.4, temperature, I want you to, and it has to be Celsius because we deal with Celsius with most of what we do. It's 37 degrees. So those are two numbers I want you to know. And then when we talk about the net worth of ATP, 30.5 kilojoules per mole. Okay, any questions so far? Be able to think about the relationship between pH and pKa. I'm going to sort of come over here to our homework questions, right? You are likely to see a question where, hang on, I'm going to move you guys out of the way here. You're likely to see a question where you're going to see a molecule. You'll either need to know what the pKa values of functional groups on that molecule are, or I'll tell you pKa values, and then I might ask you a protonation state at a certain pH. So that, again, is the relationship between pH and pKa, is it allows you to think about protonation state. Right, the Henderson-Hasselbalch equation is at its core a relationship between pH, pKa, and quantities of a weak acid and its conjugate base. We just sort of already addressed this question. Thinking about buffers, how would you choose a buffer system that you want? We already talked about the two important things that you need to think about for buffer capacity, right? And understanding at its core how buffers work. And we can revisit some of that tomorrow. The only thing that we really have left of significance from our lab math is working through some buffer calculations. I wouldn't really worry too much about this. I don't believe I have any questions on your exam about this, but thinking about how to read a graph, this is going to be one of those skills that's going to be just important, sort of moving on through the course. Let me find where that slide is. We didn't actually go through it. I gave you guys a handout for it. But it is going to be important to understand how to read graphs, what it means when we have vertical versus horizontal lines, and when those vertical or horizontal lines intersect the lines that are on our graph. What does that mean? Importance of halfway values. Okay, those are going to be really important pieces. In this case, since we were talking about acids and bases, we were really talking about pKa is the pH that you need to be at for half of your molecules to be protonated. So that's sort of these two pieces here. And I think you have a question. Let me go over here on, I guess they don't have it specifically here. Thinking about, let me go to your notes here. Thinking about thermodynamics. You want to be able to think about, for the three parameters that we think about for thermodynamics. And I would even say, if you wanted to imagine as a study guide, making yourself a table that talked about maybe 3 columns that are for enthalpy, entropy, free energy. And then let's say your rows are going to be what letter corresponds to that term, right? Enthalpy is H, entropy is S, free energy is G. If you had to think about a single word that you could sort of describe those processes or those terms, right? For enthalpy, you might say exo or endothermic. That's a single word. If you were to describe a single word for entropy, you might say disorder. If you were to describe a single word for free energy, you might say spontaneity. So I would say good study strategy would be make a table. Again, 3 columns for your enthalpy, entropy, free energy, letter, 1 word to describe, phrase to describe. Here's the phrase that we've described: bonds, intermolecular forces, and interactions for enthalpy, more molecules moving more for entropy. And then for free energy, whether and how much. Those are going to be phrases that help us think about those processes. And then also be able to tell me the sign of a spontaneous process, right? For enthalpy, or I should say a favorable process. A favorable enthalpic process is exothermic, so delta H is negative. A favorable entropic process has an entropy that is positive. And overall, a free energy that is negative is going to represent a favorable or spontaneous process. Here again are the 2 thermodynamics equations you need to know. Delta G equals delta H minus T delta S. And then delta G equals minus RT ln of K. Okay. Let's see, back to our study guide here. The single letter that we talk about with kinetics. So kinetics really refers to how fast. Thermodynamics is how much in weather. Kinetics is how fast, right? That delta G double dagger tells us the activation energy, essentially, that we need to get to the transition state. So you can think about it as, if you really want to think about it from a like a frequency standpoint, the higher the hill, the less frequent you'll have enough energy to get up and over to the other side. And I'm going to say a lot of these things will tie together with this piece down here that I'll get to in a minute, which is thinking about a reaction coordinate. Importantly, conceptually, understand the difference between thermodynamics and kinetics. Thermodynamics has to do with whether a process occurs and how much product you make, and it thinks about energy in terms of enthalpy, entropy, and free energy, right? You can have a very thermodynamically favorable process that's very slow. Hence the specific example that we talked about with ATP. So we'll go to and look at that specifically in just a minute. So thermodynamics is whether and how much. Kinetics is how fast. We talked about, and we've had some examples here, talk about equilibrium shifting. How do we shift equilibria? Importantly, what does it mean if we add or remove a reactant, add or remove a product, remembering that we can treat heat as though it were a reagent. I'm going to come over here and we'll highlight. I'm going to go through the homework in just a minute, but one of your homework problems, does a little bit with thinking about equilibrium shifting, and it has sort of heat as part of that. So I'll take a look at the homework in just a minute. See if you guys have any questions on that. We just finished just the other day thinking about intermolecular forces. So for intermolecular forces, be able to rank the 4 that we talked about: London dispersion forces, dipole-dipole interactions, hydrogen bonding, and then ionic or electrostatic interactions. And again, we'll highlight where these are as I flip through the notes, right? Just be able to rank those, and if needed, give a simple example of where we might find those. We talked about solubility, right? And we discussed it essentially from an energetic cost-benefit analysis. So let me just flip to those slides for a second so we can see them. I want you to be able to think about case study questions. I want you to think about the enthalpy and entropy that are involved in solubilizing something. And anytime we're dissolving something, we've got solute and solvent. Until we mix them together, solute is just hanging out with other solute, solvent is just hanging out with other solvent. So if we want to mix something together, we need to break up these friend interactions. That's always unfavorable from an enthalpy standpoint. But when we mix them together, they have the potential to form new interactions. So that's favorable. So sometimes we call these things compensations. So there's an enthalpy compensation. It costs us enthalpy to break things apart, but we get enthalpy when we put things back together. And then I want you to think about the competing aspects of entropy. If I take a salt crystal that's nice and ordered, and I move all of those ions throughout solution, that's very much increasing entropy. That's favorable. On the flip side, though, now I'm asking all of my solute to become very ordered around each of those solute particles. That's unfavorable. Again, I'm never going to use this sort of a thought exercise to get you to explain whether or not something happens or do math with it or anything. But I want you to be able to think about when we have enthalpy, we're talking about it being a cost if I disrupt interactions, and then a gain if I make interactions. And then from an entropy standpoint, think about how whatever process you're doing could make your system more disordered or less disordered. And a big piece of that is thinking about the whole more molecules moving more. Okay, that's increasing entropy. So that's sort of what I mean here about the solubility piece. Hydrophobic effect. That was sort of the next slide here. I would know in words and be able to write down what the hydrophobic effect is. So take 3 minutes and just say it 12 times, the tendency of nonpolar substances to minimize their contact with water. That's what the hydrophobic effect is, right? And then we've got several examples here of how the hydrophobic effect drives structure. In this case, drives structure of micelles with fatty acids and lipid bilayers with phospholipids. So it's fine if you remember or give me an example, but if I ask you, what is the hydrophobic effect? I want the definition. So give me the definition of the hydrophobic effect. Tendency of nonpolar substances to minimize their contact with water. So I'm going to pause there for a second, come back and see if anybody wants me to sort of drill down on any more of these a little bit more. We'll certainly revisit them in a minute when I sort of look at the homework and look at notes. All right. Last piece, like what might be some of the larger skills that you need to perform specific kinds of questions? And some of these I've already sort of talked to you about. Determining a protonation state. That has to do with this relationship between pH and pKa. You are going to see a problem where I'm going to give you a molecule that you haven't seen before. And you're going to see functional groups that are there. And based on what you know about functional group pKa values and the pH that I tell you that you're at, you'll have to determine the protonation state of that molecule. Okay? We'll come back to this in a minute, and I'll talk about it in more detail. You do have a reaction mechanism that's on there. It's one you haven't seen, but it's an application of concepts you already know. And I know that it's terrifying for some of you because you're like, just give me like number 1 through 9. I'd be fine with that. But as I've met with each one of you and sort of talked about things, the goal is that you become competent enough with mechanism and you understand these governing principles so that you can apply it to any unknown system. I'm going to get to these guys as we look through the notes. We'll talk specifically about reaction coordinates. You are going to have to draw a reaction coordinate on your exam. Okay, so we'll run through that. Thermodynamic calculations that allows us to think about spontaneity and equilibrium. So we'll look at a homework question that sort of connects with that. Equilibrium shifting, right? The whole concept of what we had in our aspirin overdose case study had to do with equilibrium shifting. And then again, using intermolecular forces to predict or compare certain properties. So if you're talking about which one of these is going to be more soluble in water, you're looking for the things that have more similar properties to water so that they're more polar. They're going to have more ability for dipole-dipole interactions. We really didn't talk about this too much, but hopefully it makes sense that when we talk about melting temperatures or any phase changes, going from a solid to a liquid or a liquid to a gas means we are disrupting intermolecular forces because we either have to take a very ordered solid where molecules are sitting very still, very extensive Velcro, if you will, between the two different or the molecules. When we heat up that compound, right, we provide enough energy to those molecules that they wiggle around enough that they can start disrupting intermolecular forces. And then we become a liquid. And now those molecules are still sort of connected to one another with Velcro, but they're sort of rolling around on one another, taking the shape of the container. They're going to be a liquid. Now, when we become a gas, that means we are going to completely disrupt all of our intermolecular forces. Those of you who are in PChem, I've heard Dr. Brown say we're doing PV equals nRT. At some point, you're going to be talking about ideal gases, right? Ideal gases are gases that don't recognize or realize they have neighbors. They've completely separated their Velcro from their neighbors, and they behave like they don't have any neighbors. Okay, so rank your intermolecular forces and be able to use them to think about properties like solubility or melting temperature. And you had a homework problem that's sort of related to that. So I'm going to pause there for a second, see if you guys have any questions. And then what I think I'm going to do is I'm going to go through the notes first and just kind of highlight as I look through the notes, just if there's something that I haven't already mentioned, I'll make sure to call attention to it for you to sort of make note of in your notes. But before I do that, any questions? All right. And bear with me. I'm going to go back to the beginning just because I want to make sure that there's nothing that I skip over. Mechanism. And I think I've talked to almost every one of you individually. This is kind of an important slide to think about because it kind of has a lot of the key concepts that allow you to think about what's going on with mechanisms. You know, if this is my two starting materials, right? And this is my product, right? I can see that I'm doing a substitution reaction. If this is my starting material and this is my product, I can see that I've done an addition reaction. I've formed a new bond that I have here. Anytime you're forming a bond, you can immediately identify something came in with electrons and that was a nucleophile and it went to an atom that was an electrophile. Of the mechanisms that you've done so far, 1 through 7 all have a nucleophile reacting with an electrophile. And with the exception of mechanism 1, where the electrophile was a proton, we're often going to see that the electrophile is a carbonyl containing carbon. Themes that we see, you form a tetrahedral intermediate. Now, I don't explicitly have it shown on this sort of oversimplification, if you will, of all the things that we do. But a lot of what we see is proton shuffling. So we might need to be deprotonating this nucleophile so it's not a good leaving group and protonating this Y group because we want it to be a good leaving group. So those are some of the themes that we see. I encourage you guys to think about starting to work through that extra credit assignment, sort of the meta-analysis of mechanisms. It's going to allow you to start trying to see these themes in terms of things that we're going to cover. Reaction mechanisms 4 through 7 all dealt with molecules where Y was not a good leaving group. It was either an aldehyde and we would make a hemiacetal and then an acetal, or it was a ketone where we'd make a hemiketal and then a ketal. So the only options when Y is not a good leaving group is after we form our tetrahedral intermediate, we protonate that carbonyl oxygen that is now an alcohol. Okay, so I encourage you, our exam is not going to be until next week, Monday. Now, again, if Monday is Hearst Day, we will have it Wednesday. But certainly I encourage you over the next couple of days, if you're still feeling like you're fuzzy on mechanisms, you want to go over something, don't hesitate to try to come find me. So that's mechanism. All right. We sort of talked about this piece. You do need to know sort of this main fuel equation. Some important pieces to make sure you don't make a mistake on. If you had to give me this equation, don't write an equilibrium arrow. You guys are very used to writing those because that's what you have for your mechanism. But we are not plants. We cannot take carbon dioxide, water, and energy and make it into carbohydrates for ourselves. Okay? So that's that basic equation. You don't need to know anything about functional groups with the exception of what you needed to know from your fundamentals quiz. So be able to know the structures of certain functional groups, and for those that have relevant pKa's, what those are. You are going to need to apply that information to tell me the protonation state of an unknown molecule. So by unknown, meaning a molecule you haven't seen before. We talked about this slide. Keep in mind when you're doing mechanisms, when you're doing protonation and deprotonation events, you can always just use water. But if you want to use hydroxide, make sure you only use hydroxide in water. If you want to use hydronium, make sure you only use water and hydronium. You never want to have a mechanism that has hydroxide and hydronium. There's not a pH that exists where you're going to have high concentrations of both. Or, as is often the case in my mechanisms, my keys, you'll see that I use HB plus and then B as my acid and base species respectively. Sort of talked about the ability to write acid or base equations, whether they're strong acids or weak acids, and so forth. We talked about this. That's kind of reminding us of that relationship. Again, the Henderson-Hasselbalch equation is kind of a mathematical sort of application of this. I'll get to homework in just a minute. Talked about this slide. You are going to get this table. Okay, so think about the different ways that you could use this table, whether it's qualitatively picking a buffer that you want to use, whether it's quantitatively being able to use a pK. Now this, sometimes they don't say pKa in some of these tables and stuff that I use. So this table could be used for many different pieces of information. We'll talk again a lot about buffers tomorrow in lab math, but conceptually understand how buffers do their job. We highlighted and then saw an application of in our aspirin overdose case study, how we think about buffering capacity. Okay, match when these are approximately equal, and that happens when you match your desired pH to the pKa of your weak acid conjugate base system. That's going to be one of the best buffers. And then here's a number that I want you to know. You want to have buffers that are greater than 10 millimolar to effectively be buffering. All right, we talked about this. You do need to know the Henderson-Hasselbalch equation. You can use it to calculate, and right now, we'll talk tomorrow in a lab class. When you're using this to calculate amounts of a weak acid that we're going to do in lab, this is a little bit more complicated than I would ask you to see on your test in lecture. Those problems take a good bit of time. I want you to know how to do them, but you're not going to see that on a 50-minute test in lecture. It's just, I mean, they're like 10, 15-minute problems, and that's not worth my time to ask of you to just have it on one problem. But you are likely to not only need to know this equation, but be able to think about using it to calculate pH if you know the concentrations of things. So think about it in that way. Talked about that guy. Again, put giant stars all around this slide. This is kind of one of those key important slides. I'm going to go over here just for a second because I do believe if you go to the Blackboard page, that some videos that were ones that were made more recently. So they were made a couple of years ago. Again, there's the graph interpretation one if you wanted to watch that. But ones that I would highly recommend watching again are this blood buffering system. And again, with these, I also have sort of the finished slide that you have after I recreate that. So that's the slide that's important. It looks just like what you have in your notes. But this video is, you know, an 11-minute video that creates that slide. So you'll sort of hear it in real time. So anything that are those sort of more involved slides. Here again is a thermodynamics one. I should probably I'm going to do this when I do my new system for sort of organizing things. I'll always make sure to have sort of the finished slide product here. But remember, I told you a good study tool might be to make that table to think about thermodynamics. That's based on that slide. This is a recreation of that slide. This is a recreation of the reaction coordinate information. So again, that might be another good one to watch. So those are three sort of big concept things that it might, you know, do well over the next, let's say, week. Well, I guess it's 5 days until we have our exam. That, you know, maybe watching one of these a day could be a way, particularly if it's a concept that was a little fuzzy for you. All right, so that's, again, one of those big ones that there's a video on that. We'll go through homework questions in a minute. Let's see more on functional groups. So this is another one that there's a slide for, kind of recreating this slide and thinking about thermodynamics. Be able to, if I gave you either a generic equation like this, or if it was a specific equation, could you write an equilibrium constant from an equation, right? That means taking and multiplying together the concentration of your products raised to powers that are exponents, and then divided by the concentration of reactants raised, multiplied together and then raised to powers that are exponents, right? So if you had to write an equilibrium expression for any equation that I give you, make sure to omit solids and pure liquids. And again, that's how the equilibrium constant plays into sort of free energy and spontaneity here. Another equation here that's important to think about. Be able to think about, and if you had to write a rate expression, we're not going to do too much with rate until later in the semester, but rate expressions, the important take-home piece from this is when we're talking about how fast a reaction goes, it has nothing to do with how much product we have. It has everything to do with how much reactant we have and what the order of the reaction is. Now, something that's going to be unique, you don't need to know this per se for the exam, but I just kind of want to set things up for you. One of the things that's common in biochemistry is that we'll see things where the reaction order might be 0. We talked about this in general chemistry, but you never really did many experiments or saw many problems that had that. Remember what it means to be a reaction order of 0. It means if I change the concentration of that species, my reaction rate does not change. And we tend to see that a lot with enzymes when you have, let's say, saturating concentration of substrate. It doesn't matter if you add more substrate, it's not going to change the reaction. So the reaction rate is actually, or the reaction is 0 order with respect to that. But not a lot that you need to do with this, but be able to take a generic equation, write a rate expression, and importantly, kinetics tells us how fast, okay? This is, again, a money equation or money slide. Put giant stars next to this slide. If I come back over here, if you need some help sort of thinking about that, there is a video that you can watch on thermodynamics, kinetics, and then the reaction coordinate. And I think that video might actually go beyond here and also think about a specific example of putting all of those pieces together and understanding how ATP, which is our biological money, is valuable. That has to do with the size, the magnitude of delta G. It's stable. That has to do with the magnitude of delta G, but it's accessible. That has to do with the ability of enzymes to lower the transition state energy, making for a smaller delta G double dagger. Okay, so those are 3 sort of really important money slides. We've got sort of that main sort of equilibrium shifting, breathing, fuel metabolism sort of connection of equations. We've got reaction coordinate, and then why is my brain not working? Yeah, I guess just thinking about it's still thermodynamics, but thinking about sort of that thermodynamics table, if you will. I'm not going to ask you questions about the Van Hoff plot. A lot of this was to recognize, measure things you can measure, plot things as a straight line. That's a theme that we're going to see. All right, what do you need to know from the aspirin overdose case study? I would say in general, not anything specific, but you may need to apply concepts to a new system. So for example, looking at a molecule and labeling functional groups, okay? I don't expect you to be able to repeat and do that with aspirin. You don't need to know the structure of aspirin. Need to know how to do a mechanism, right? This is more complicated than you're going to see. This is a multi sort of step piece, but all of the concepts that we've applied and thought about are here. Again, I do want you to think about solubility, how charge affects solubility. And if you were to see and in this example, I'm not going to give you aspirin, okay? But if you saw a drug that you didn't know about yet, or you didn't know what it was, but you can see the structure of it, so you know the functional groups that are there, could you choose whether you wanted to do a gastric lavage at high or low pH, depending on, okay, if I want to have high solubility in water, I want my drug to be charged, not necessarily negative, it just needs to be charged. But could I then say what pH I'd need to be at in order for that to happen? Now, in this specific case, in our aspirin overdose case study, aspirin is neutral when it's protonated. It's negatively charged when it's deprotonated. So I needed to deprotonate my aspirin in order to make it be charged so that it's more soluble. Okay, that is a specific example of the concept in our aspirin overdose case study. Be able to think about and apply concepts in a situation that you don't know about yet. Again, the Henderson-Hasselbalch equation in that case was used to look at the ratio of the amount of weak acid to conjugate base, the weak acid again being aspirin. So that was Connor and Allie's questions. Let's see, Lee and Liv were sort of dealing with the equilibrium shifting piece, right? So their questions were fairly qualitative, sort of thinking about that really important slide that kind of shows the integration of those different concepts. Connor, you asked the question. So again, here's the answer. That bicarbonate drip is necessary because we've depleted that bicarbonate because essentially we're breathing it out as CO2. And we went through this, the last part of the case study, and highlighting you will not be asked specific questions about the aspirin overdose case study. But a lot of the things that we learned about and used to answer questions in the case study, you may need to ask or know how to do them in a new situation. So this last question had to do with using the Henderson-Hasselbalch equation to understand how changes in pH are going to affect the ratio, again, of a weak acid and a conjugate base, but now it's the bicarbonate and carbonic acid that's in a patient's blood. So that's sort of what this last piece is about. And this kind of harkens to the important point of this is problematic from a patient standpoint because one of the components that we use to buffer our blood is getting way skewed from being an equal-sized army. And we're also depleting the size of the army. Again, that's why the bicarbonate drip is necessary. But that sort of a situation is such that we're not having a good buffer. Good buffers have relatively equal amounts of weak acid and conjugate base. And I want you to remember that number of 10 millimolar. You have something that's less than 10 millimolar, you're not buffering very well. All right. Here again is that slide on intermolecular forces. You do need to know these names, right? And you need to be able to rank them from weakest to strongest. Kind of understanding their prevalence. It's sort of inverse with their strength. The weakest one is actually the most prevalent because everybody has London dispersion forces. Very unique cases to have electrostatic interactions. They're not all over the place, okay? But that's also the strongest interaction. And again, we talked about some examples of where we might see those. So I'd put a little star on that slide. That's an important slide. We talked about solubility as a cost-benefit analysis from a thermodynamic standpoint. And these last few slides, I'm going to flip through them quickly. I don't believe there's any specific questions on them, but everything that I sort of mention here is a topic we're going to revisit later, which is why I put a slide early in the semester on it, so that when we revisit it, it's not the first time that you're hearing it. So osmosis and diffusion both move things with their concentration gradient, so they dissipate concentration gradients. The difference is whether we're moving solvent or solute. Solvent, again, in biological systems, tends to be water. Oh, we did talk specifically about sort of the red blood cell sort of example there. And we will see this again by moving solute when we talk about facilitated diffusion. This was a slide we spent a little bit of time on. I would want you to be able to, if I were to ask you to do an experiment, and I would say, what do you think is a model single cell eukaryote that we could do? Okay. Oh, that was yeast. So know things like eukaryote, I'm sorry, E. coli is a model single-celled prokaryote. Yeast is a model single-cell eukaryote. Those are really good because short generation times. If I'm looking for the effect of something, I don't need to wait 3 years for an organism to sort of grow up. Happens very quickly. Okay, then we talked about worms, we talked about fruit flies, we talked about fish, mice, dogs, humans, right? These guys are nice because they're multicellular and invertebrates. That's good because then I don't have to worry about ethics boards looking into the research that I'm doing. Once you start having a backbone, so all of these are vertebrates, then you start having issues. So 2 specific examples here that I want you to know. 2 specific examples I want you to know here, but there's lots of things that can fall into this multicellular invertebrate category, but these are 2 common ones. And then the host of things that people do experiments on that are vertebrates is huge. So you could almost put anything in that category. But I do want you to know those sort of different model organisms that we might see as we're looking at different sort of biochemical pathways. Do not need, again, don't need to know anything about taxonomy and phylogeny for the exam. Okay. Terms that we're going to see time and time again. So we just sort of bring them up. Concept of evolution, we sort of talked about that. You're not going to see questions on this billion-year-old war. All right, so that was it. And again, even though we had this last little piece where there's that that big chart that kind of walks through the different biomolecules, that is meant to be a resource sheet that we'll use as we go throughout the course. So not something you're going to have specific questions on. Before I go over homework real quickly, does anybody have any questions on anything from the slides? Okay, let's go back here. Almost done here. This won't take me long to go through this. I just want to highlight if there's certain things that you are likely to see questions on from your homework, just kind of drawing attention to that. So 100%, you're going to see a problem where I give you a molecule. You either have to know or you are given pKa values and you have to tell me what the protonation state is. Okay. Questions like this, if you know what the pH is and you're looking, you just need to match pH and pKa to make the best buffer. If you're looking at saying which buffer would be the best and it's a small and a large concentration of buffer, large concentration is going to be the best. So just some qualitative things using that table. Tell me what you think the best buffer system is going to be. You will see a problem like that. Be able to do these kinds of calculations. You will see a problem like this, where you're going to have information where you'll need to use these 2 equations. So again, delta G equals delta H minus T delta S, and then being able to interconvert delta G and K. Okay. So this was just a homework problem that allowed you to sort of practice that. Think about spontaneity. Again, spontaneous reactions are going to have equilibrium constants greater than 1. Non-spontaneous reactions, just by the nature of how this math works, are going to have equilibrium constants that are smaller than 1. Homework question here.
Dr. Perne,
Yeah,
will we be given the R value or do we have to
100%.
memorize it?
Nope,
Okay.
you do not need to memorize that. You will be given R value. I don't give you 273.15. I don't tell you how to convert Celsius and Kelvin. I do expect you to know that. And if you saw a problem and I told you it was at physiological temperature, I'd expect you to know that that was 37. Okay. Good questions. Again, equilibrium shifting. Generic equation here, but if you had to think about a specific example, right? We see that equilibrium shifting with that equation to deal with carbonic anhydrase and then carbonic acid dissociation. And if there's any of these, hopefully you guys have all worked through your homework. The goal, even though your homework isn't technically due until we have an exam, is that by the time we have a review session, you've done the homework, because that's going to be the best opportunity for you to ask for clarification on something. And that works best if you've sort of worked through your homework. You will not see a question where I'm going to ask you like super specifics like this one was. But if you were to see molecules, right, and had to sort of predict solubilities, right, think about like dissolves like and so forth. So you were looking up solubility values on these molecules and seeing if they sort of made sense. And hopefully, the least soluble is going to be the one that has the most nonpolar character to it. So that's all that we had for that problem. And this question really is sort of related to, I'm going to flip back over here. I come back to the beginning when we had this guy. Super important slide, right? That homework question is basically relating these different things. All right, I think there might have been I've had different sort of like homework sets, and it is not a good use of my time to probably rewrite my homework sets. So I think you guys had one more problem, or did you have two more problems on your homework set? You guys remember? I think you had, because that's the same problem. Did you have this one? I think you had the one, because I've talked to a couple of you about how many grams of sodium succinate and disodium succinate. I think that's one that's on your homework. Did you have this one? pH of a solution that's 2 molar acetic acid with 5 grams of sodium acetate? Yes, Connor's saying yes. And then I'm pretty sure you had this one. What's happening when this is kind of a neat lab question. So you make and this for real can happen with something like tris. This is why people tend to avoid tris buffers in lab. You may see heaps more often. The dissolution of tris, or I should say, sorry, the dissociation of tris, because tris is a weak acid, is actually an endothermic process, which means there's a heat aspect to it. Heat is a reactant. So there's a temperature dependence of the pH of this buffer. So this is just kind of a neat problem that allows you to actually think about that from a qualitative standpoint, but then make a little reminder if you actually are using tris buffers, that if you're changing the pH significantly from the pH that you're preparing the buffer, you may affect your pH. I'm going to put a pause in if anybody has questions on these two from if they're on your homework. Let me just do this right now because I don't remember. I know Connor was nodding yes. I want to remember for myself. So here's homework. Yeah, so you have, yep, you have both of those problems right here. So if you have questions, yes, and you have this guy as well. So if you have questions on those, let's get through lab math tomorrow on buffers. And then if you still have questions about that, we can actually go over it tomorrow. So I'm going to stop talking because I want to see if you guys have questions, but that is sort of everything I think I was going to talk about and go through sort of tonight. Let me go back and just look at my slides here. I don't think there's anything else. Any questions? No? Well, and part of the reason we do this, not the night before the exam, is it gives you guys some time to study, digest stuff, and so forth. And then if you have questions, there's still time to sort of visit with me and ask questions or clarifications on things before we have our exam. I don't know. Do you guys have a gut feeling for Hearst Day? I don't know. I'm feeling like it's Monday. I was looking at the weather again, and it's like it's supposed to be beautiful through Monday. But then let's see this week. Well, actually now it looks fine. There was potential. Well, I guess they say there's a 24% chance of rain on Wednesday. Monday, 4% chance of rain. So
I'm thinking my gut's telling me Monday, but my gut has always been one day off every single year.
now,
So
when you actually say one day, do you think it's
one like
One
class
Monday.
day, not as
Okay.
like Tuesday or Thursday. Yeah.
Got it. All right. Well, we'll see what your gut is saying. My gut is sort of saying Monday too. But I don't know. I already moved my Gen Chem quiz to Wednesday, which I was going to give them an extra day for anyway, but I don't know. So clearly if it's Monday, then this exam is Wednesday. And we'll adjust from there. All right. I don't want to keep you guys any longer. Let me know as you study if things continue to come up, and then remind me to talk to people tomorrow and make sure that everybody has, if you are interested in taking advantage of it, either the ability to come in at 8:30 or stay till 9:30. And if not, we'll figure out what that means in terms of whether or not you want to take. You have to, I do want everybody to take it the same day, but we could potentially move it around a little bit to accommodate what your class schedule might be. Okay? All right. Good night, guys. I will see you tomorrow. Some of you bright and early. Maria, who else is with me bright and early? Madison is. Yeah, we're going to meet at 8.
Okay.
All right. See you guys. Bye.
Bye. Thank you.
Yep. Did you have any questions, or no, you're just trying to sign off? I just didn't want to leave if, all right, bye.